Oh, thank you for the session chair. I will start my presentation. Hello, everyone. I'm Tianzhe from Shanzhao University, and it's my pleasure to share our work on targeted adversarial attack on knowledge graph embeddings. Firstly, let's quickly go through the basic background of our work. A knowledge graph embedding, KGE, is quite familiar to us. However, they are fragile to KGs with low data quality, but they are very common in our real world. On the one hand, many deployed knowledge graphs, especially like cybersecurity KGs, are under frequent attacks on purpose. On the other hand, with the explosive development of automatic KG construction techniques like relation extraction, errors can be hardly prevented. Under such circumstances, KGE methods might then bias the embeddings and further throw negative impact on real-world applications. For example, in an entity query scenario, if a triple James Cameron direct Titanic is removed, we are likely to miss the correct answer of the query, which movies directed by James Cameron have won the Academy Award. So, in order to systematically investigate how KGE methods perform when such issues occurs, some studies try to employ adversarial attacks, and this is also offer a good way to understand the robustness of KGEs. The attack behavior of adversarial attack on KGE are mainly including adding noise triple to the original graph or deleting useful ones, and this is also known as the data poisoning attack. Unlike many works developing good KGE methods, effective attacks are expected to decrease the performances of KGE-related tasks like link prediction. It's worth mentioning that the researches about the adversarial attack on KGEs are relatively limited, which all develop target-oriented attacks. In short, we can call them targeted attackers. As shown in the upper right dot box, targeted attackers required access to target triples in advance, which is a part of the original testing triples. Besides, target attacks rely on KG embeddings learned by a certain KG method, and this falls into two main limitations. Firstly, it lacks practicability in the real world and cannot explain general regularity of KGs. To overcome these limitations in our work, we develop untargeted attack, different to targeted attackers. In our sightings, none of the testing triples is accessible during the entire attack procedure. Also, we aim at reducing the global performance of all testing triples rather than a few selected targets. Next, I will show more details about our work. To get rid of employing KG embeddings learned by a certain method, we seek to extract useful structural patterns, and in this work, we deploy logical rules that can be learned from KGs. To be more specific, we utilize first-order Horn rules in the form like this. Both rule body and head is composed of several single atoms, where R denotes the predicates of the atom that can be assigned with relations in the knowledge graph, and X, Z, and Y are called variables that can be grounded to entities. Logical rules can well describe the knowledge of a knowledge graph, and a knowledge graph structure is highly associated with its rules. Also, when the KG structure changes, as some useful noise triples are added or useful triples are deleted, the rules will correspondingly changes, and vice versa. So, we developed the overall framework of our untargeted attack with the help of logical rules. To begin with, we first apply a rule learning method to extract rules from the knowledge graph, and then we implement deletion and addition attack respectively. For deletion, we remove triples which support the grounding of high-confidence rules. With the absence of such triples, many trustworthy rules will be missing, so so that the global feature of the entire KG can be fragmented. So we assign every triple an influence value, which is the pooling of the contribution of the triples to supporting the learning of rules, and select triples in line with their ranks on influence values to delete. In the addition attack, added perturbations are expected to mislead KG methods, capturing unreliable rules rather than reliable ones. Therefore, we disrupt the extracted rules with low confidence to get a series of negative rules. When disrupting rules, we utilize predicate rewriting strategy. That is, we replace the predicate in the rule body by another relation with the highest correlation values between them. The correlation values are determined by the co-occurrence of a relation and its neighbor relations. After that, we generate perturbation triples via inferences of the negative rules over the knowledge graph. We carry out our experiments on the impact on link prediction task over 3 representative type of KG methods. Also, in order to implement target attacker baselines without the direct access to testing triples, we randomly select a subset of the original training triples as the targets. From these 2 tables, we can find that in both deletion and addition settings, our method achieves competitive performance in decreasing link prediction performances of all KG methods. Since our method uses rules to create the attack, we compare the rules extracted before and after the attacks. We conduct a statistical analysis of the confidence distribution of extracted rules with different rule heads, and examine the attack impact on the link prediction result for them. From this figure, we conclude that the decrease of link prediction performance tightly associated with the violation of logical rules. As for the figures on the right, we directly compare the robustness of different types of KG method and have some interesting findings, such as GNN-based KG methods show relatively greater robustness to the addition attack, and this indicates that the graph structure matters more to the robustness of method using GNNs. Besides the general comparison, we also focus on the robustness of a single KG method to 2 different types of attacks under different perturbation budget. Here we select the result of 2 typical models, Trans-E and dist mode, to show. We can see that Trans-E is more vulnerable to added perturbations. It is easily affected by the injected noise and the biased KG representations. To further figure out how the attack leads to such results, we explore the changes of specific embeddings learned by Trans-E. Here we select several relations in the same relation pattern. For example, the relation 3, 4, 5 are in the categorized into the same relation type, and examine their cosine similarities before and after attacks. From this heat map, we find that in adversarial addition, Trans-E cannot well identify relations of the same type. As we can see, they just obtain low cosine similarities, and this analysis suggests the importance of distinguished relations of different types for improving the robustness of KG methods. To figure out how the implementation of rules influence our attacking performances, we also conduct several experiments. And in this part, we investigate the impact of the length of our used rules on the attacked performances. As we can see, although rules with 3 lengths exhibit a more complex pattern, it brings an inferior reduction of the link prediction. and this implies that the conjunction of two atoms may be the most common symbolic patterns in KGs. In the adversarial addition attack, we disrupt the valid rules by rewriting one predicate of the rule body based on the relation correlation value. To verify the effectiveness of this module, we compare it to the random replacement of relations, and this table also can demonstrate the effectiveness of our predicate rewriting strategy. That's all my report. Thank you for listening.